All right, so as promised, I want to now use molarity more in the context of solution stoichiometry. And I'm sorry that this part of the question got clipped on the previous page. I've made a copy so we still have the text of it and can solve this. But before we even get into it, I just want to orient you with a similar image to what I tried to put in your last lecture notes, but updating it for stoichiometry. So we have in this class so far been getting more comfortable with taking grams of a compound and using the molar mass as a conversion factor to go back and forth between grams and moles of a thing. And we've also gotten kind of comfortable with using chemical equations to build mole ratios that relate moles of things to other things. What's new in the solution stoichiometry piece is that now we know about molarity, single big M, and molarity is a way that allows us to go back and forth between moles of a thing and volume of a thing in liters. Of course, we can use metrics to go into milliliters if necessary. So the only thing that's new in solution stoichiometry is that we have a new way to dig into or out of the mole tunnel. So we can use molarity to take a volume and figure out moles of the solute in it, or to take moles of a product and calculate what volume of the solution you would need to move it. So let's see an example here. Here we have a reaction described where we have some aqueous substrates, we have some aqueous reactants, and they are reacting to produce a solid, which is called a precipitate. When you mix two clear liquids and a solid comes out of solution, that's called a precipitate. And so this question says, when aqueous magnesium chloride is combined with aqueous silver nitrate, a precipitation reaction occurs. We're really going to talk more about those next week. What would be the theoretical yield of the solid? So I'm making my if table. Here's my solid. How many grams of that solid am I going to form from 25 milliliters of a 0.4862 molar solution of magnesium chloride, assuming you have excess silver nitrate. So I have more than enough silver nitrate. I'm going to focus on the magnesium chloride and figure out how much silver chloride I can produce. Well, I know the target. I know what I'm trying to get out of my tunnel. How do I dig into my tunnel? I encourage you all to immediately, when you see big M, change it to moles per liter to remind yourself this can be a useful conversion factor, getting back and forth between volume and moles. I'm given a volume of that solution, so that's where my tunnel is going to start. I'm going to start with 25 milliliters of magnesium chloride. Now I know that molarity is moles per liter. So the very first thing in my tunnel is going to be to get out of milliliters and into liters so that I can, as with any stoichiometry problem, dig into that mole tunnel, get out of liters of that compound and into moles of that compound. So at this point, I have a tunnel that's gotten me into moles of magnesium chloride. Where should I go? Well, the whole reason to get into moles is to exchange moles. So I need to go to something else. What am I trying to relate to? I want to know my theoretical yield. So I want to get out of moles of magnesium chloride. I'm going to exchange for moles of that product, silver chloride. Now my theoretical yield, I can't measure out moles on a balance. I can only measure out grams. So I'm going to get out of moles and into grams as my theoretical yield. Now that I have a tunnel going to the unit that I want, now I'm going to worry about plugging in the numbers. So here's a metric. Milli is tiny, 10 to the negative 3 liters per milliliter. Here's my molarity. Again, 0.4862 travels with the moles of magnesium chloride. it's assumed that that is per 1 liter of solution. So when you see molarity as big M, this number travels with moles per 1 liter of solution. The mole ratio comes from my equation. For every 2 moles of silver chloride, I need 1 mole of magnesium chloride. And then the last one is a, excuse me, a molar mass, which I need to calculate. So on my periodic table, silver is 107.87 and chloride is 35.45. So I got 143.32, 143.32 grams per mole. Plug into my calculator. So 25 e to the minus 3 times 0.4862 times 2 times 143.32. And I got 3.4841 something, something, something. So now it's time for sig figs. 4, 4, 5. I get to keep 4. 3.484 grams of silver chloride. So all that's different in solution stoichiometry is that now I have this new conversion factor of molarity, which is useful to dig into the mole tunnel from a volume of solution. I want you to pause the video and see if you can set up a tunnel for this next one based on those same principles. How many milliliters of a 1.46 molar sodium hydroxide solution is needed to fully react with a solution containing 8 grams of aluminum chloride? Pause the video, set up your tunnel, maybe unpause the video and see how the tunnel looks, and then put in the numbers and solve for the end. I'll be here when you get back. Okay, I know that I have 8 grams of this, and I want to know how many milliliters of this is needed to fully react with that 8 grams. I know that that solution is 1.46 molar. Again, I'm going to immediately get rid of big M and tell myself moles per liter. I want to know how many milliliters. That's the ask. So I'm going to start with that amount of the other reactant, 8 grams of aluminum chloride. And I want to relate that to the other reactant. So I'm going to get out of grams of aluminum chloride and into moles, because the only way we can relate things is through that unit of the mole. And the reason you get into the mole is to exchange those moles for other moles. So I'm going to get out of aluminum chloride and I'm going to go into sodium hydroxide. I know that's my other reactant, but I don't want to know the moles of the other reactant. I want to know what volume of that solution I need to add so I can relate moles of my solute to volume of solution using molarity. But that takes me into liters. Molarity is per liter. So the last thing I need to do is get out of liters and into milliliters of that solution. Once you have your unit map, you can go through and plug in the numbers. Again, pause your video so you can get all those numbers. And I'll be here when you get back. So this is a molar mass of aluminum chloride. I'm going to solve or calculate it over here. I have 1 aluminum and 3 chlorides, 26.98, 35.45. Add those up. I got 133.33 grams per mole. So I'm going to go 133.33 grams into moles. I need 3 moles of sodium hydroxide for every 1 mole of aluminum chloride. Here's my molarity. 1.46 travels with the unit of mole per 1 liter. This number travels with the unit of mole, even if it's in the denominator. We're going to put that number in the denominator. And then milliliters are still tiny, 10 to the negative 3 liters per milliliter. I can plug in 8 divided by 133.33. times 3 divided by 1.46 divided by e to the negative 3. And I got 123.29 something, something, something. 3 sig figs, 5 sig figs, 3 sig figs. I can have 3. I need 123 milliliters of that sodium hydroxide solution to fully react with that amount of aluminum chloride. Okay, that's 2 sample stoichiometry problems. I've got 2 more to do, so maybe pause the video. Take a chance to read this next one. And then solve it for yourself. And then unpause the video. I'll be doing it back. Okay, how many milliliters of phosphoric acid, and I know the molarity of that phosphoric acid, are needed to neutralize 50 milliliters of 0.125 molar calcium hydroxide? So again, I don't need to know anything about the product. I'm not being asked about the product. I want to know how many milliliters of this, and I know its molarity, are needed to fully react with 50 milliliters of a 0.125 molar solution of calcium hydroxide. Okay. I am doing a stoichiometry. In this case, we have 2 aqueous solutions. So we're going to start with the reactant that we know, and we're going to relate it to the thing that we need to know. So I know I have 50 milliliters of calcium hydroxide. I want to relate it to phosphoric acid. I'm going to get out of milliliters and into liters so that I can use that molarity to get into moles. Right now, I have dug into the mole tunnel. I've related that amount of the reactant to moles of the reactant in that amount of solution. Now I'm going to do my exchange. I'm going to get out of moles of calcium hydroxide, and I'm going to exchange for moles of phosphoric acid. I'm going to use that mole ratio. I want to know a volume of phosphoric acid, so I'm going to get out of moles of phosphoric acid. And I'm going to get into liters of that compound, but I want to know milliliters. So I'm going to get out of liters and go into milliliters. Now I have a tunnel that gets me to that final answer. I can plug in my numbers. Milliliters are tiny, 10 to the negative 3 liters per milliliter. Here's my molarity, 0.125 moles per liter. Here's my mole ratio for my chemical reaction. So 2 phosphoric acids for every 3 calcium hydroxides. Here's my molarity of phosphoric acid, 0.500 travels with the unit of mole per 1 liter. And lastly, here's my metric, 10 to the negative 3 liters per milliliter. And plug into my calculator, 50 e to the negative 3 times 0.125 times 2 divided by 3 divided by 0.5 divided by e to the minus 3. And I get 8.3333 repeating. 4 sig figs, 3 sig figs, 3 sig figs. I get to keep 3. I need 8.33 milliliters of that phosphoric acid solution to fully react with that amount of calcium hydroxide. All right. We've been building. We've seen some examples. Here we used molarity, 2 different molarities as conversion factors. So that's why I like to line up information with the problem so that I know this molarity goes with this thing and this molarity goes with this thing. It's really useful to organize the information in that way and keep it all straight. This last problem is a doozy. It's a multi-part. I encourage you to pause the video after each part, check your work before you go on to the next part. So take it like a progression. because you got to have the first part to get the second part. And then the other parts may or may not be related, but you want to solve it sequentially. Usually when I write problems, I write them in the order they should be worked. So sometimes they are interdependent. Okay, so read the question, pause the video. When you've done this first part, unpause and check, and then pause again. Okay, I'll be here when you get back. So a student adds 50 milliliters of a solution of silver nitrate of unknown concentration to 500 milliliters of a 0.5 molar sodium chloride solution. A white silver chloride precipitate forms, was filtered, dried, and had a mass of 8.96 grams. Sodium nitrate is also produced. Write a balanced equation for this process. Okay, well, here's some nomenclature. Silver nitrate, silver is always +1, nitrate is -1. So silver nitrate is AgNO3. Sodium chloride, that one we know, it's NaCl. I'm producing silver chloride. Well, I gave you that formula. Sodium nitrate is also produced. Well, sodium is always +1, nitrate is -1, so there's my sodium nitrate. So a student adds 50 milliliters. And I don't know that concentration to 500 milliliters. And I do know that concentration. And I also know that 8.96 grams of this precipitated. So now let's see what question 2 is. So pause the video, read question 2, see how you would approach it. What is the concentration of sodium ions in the final solution after the reaction occurred? What is the concentration of sodium ions? If you're being asked concentration, this word concentration, as we discussed in lecture, concentration, when we use that in chemistry, means molarity. So when you're being asked what's the concentration, in this question, literally, you want to know what the concentration of sodium ions is. Remember, concentration is moles over volume. So sodium ions, moles of sodium ions per volume. Now here's where things can get a little tricky in problem solving and solutions. What volume are you talking about? Because you were given lots of volumes in the problem, 50 milliliters, 500 milliliters. This says the final solution. Sometimes in solution chemistry especially, I like to draw myself a cartoon. I have 500 milliliters of a 0.5 molar sodium chloride solution. And to that, I'm adding 50 milliliters of silver nitrate, and I don't know its molarity. Well, if we're being asked about the final solution, then my final solution has 500 milliliters plus the 50 milliliters that I added. So a total volume of 550 milliliters. I have a new volume in my second solution. This is my final solution. So when we think about calculating the molarity, that volume is important. In this case, it's the final volume. And we know the final volume to be the sum of those two volumes of solutions that were added. So 550 milliliters. Now, I know I have sodium ions and chloride ions in solution, and I'm adding silver nitrate. I was told this precipitates out. So at the bottom, after the reaction, I have 8.96 grams of silver chloride. But sodium nitrate is soluble and is not out of, it is all sodium salts are soluble. Why did I write AG? Okay, AQ. Sodium is still in solution. It doesn't react. It doesn't come out of solution. So all the sodium ions in solution at the beginning are still in solution at the end. So how do I find those moles? How do I find those moles of sodium? Well, where did they come from? They came from that 500 milliliters of sodium chloride. All the moles of sodium came from that 500 milliliters of sodium chloride. I need to get into moles, so I need to get out of liters and out of milliliters and into liters so that I can get out of liters and into moles of sodium chloride. So right now, my tunnel gives me moles of sodium chloride, but I don't want moles of sodium chloride. I want moles of sodium. So I'm going to do that exchange by the chemical formula. There's 1 mole of sodium for every 1 mole of sodium chloride. Right now, I have the unit that I need in the numerator. Moles of sodium. What do I need in the denominator? I need liters of solution. If you'll remember mathematically, N over V is equal to N times 1 over V. Algebraically, these are identical, rather. So I currently, all of this tunnel has given me moles. Now I can just divide by the volume, which is 550 milliliters. People ask me a lot of times when I do this, what does this 1 mean? Well, it means nothing. It's just me taking this algebraic relationship and separating the terms. I just put it up there as a placeholder, as a way to show that I'm putting that volume in the denominator. But right now I have milliliters in the denominator and I want liters to be in the denominator. So I'm going to do one last metric conversion to get that into liters. So now my tunnel gives me moles of sodium per liter, which is what I want to know. 500. Oh, sorry, I don't have all the volumes in here. So 10 to the negative 3. My molarity was 0.500. And this is the full unit analysis version. So 500 times e to the negative 3 times 0.5 divided by 550 divided by e to the negative 3. And I got 0.454545 going on and on and on. 4 sig figs, 4 sig figs, 3 sig figs. I can have 3 sig figs. So 0.455 molar sodium. Those of you who are thinking ahead and like shortcuts may have also realized this is just a dilution. Since sodium doesn't really do any chemistry, it stays in. We could also have thought about this using the dilution shortcut. We want to know the new molarity of sodium. We know the original molarity, which is 0.5 molar. We can divide by, or we can multiply by the original volume, which is 500, and divide by the new volume, which is 550. To get that new molarity, and you get the same answer. So yay you if you saw that shortcut. Both of those are valid ways to solve that problem. I'll just show you right here, or I'll just illustrate why they both work. Here is our V1, here is our M1, and here is our 1 over V2, and we are solving for M2. So that's why this works. M1, V1 divided by V2. So we basically did the shortcut, but we also added some metric conversions in there. Okay, pause the video, read the next question. See if you know how to solve it. I'll be here when you get back. Okay, if all the silver ions precipitated, what was the concentration of the solution of silver nitrate? So I want to know, what was the concentration of silver nitrate? That's what this question is asking. I added 50 milliliters of something I don't know. I don't know the molarity. And so here's where I need to solve it. So what is a concentration? Again, a concentration is moles per volume, but what volume? In this case, this is the original solution whose molarity we don't know, but we do know that all the moles of this came in this volume. So here's the volume that it's talking about. We know the volume of this solution. We don't know its molarity. So this is going to be the volume of that silver nitrate solution. We need to know the moles of silver nitrate. How are we going to find that? Let's just revisit the equation that we put information with. We know this was 50 milliliters. We don't know its molarity. We know a volume. We know a molarity. We know a mass of this. Well, look, here's silver nitrate. It became silver chloride. The problem told us that all of the silver ions precipitated. Where did it say that? Oh, it says it down here. If all the silver ions precipitated, so they all became the precipitate, they must have all gone into this mass. We must be able to use that mass of silver chloride and relate it to the moles of silver nitrate. How do we do that? We're going to get out of silver chloride and into moles of silver chloride because we want to relate that amount to moles of silver nitrate. The way we relate things is through that unit of the mole. So now I have what I need in my numerator, moles of silver nitrate. Now I just need that liters of silver nitrate. So again, I'm going to put that volume in the denominator. It's 50 milliliters of that original solution, but I need liters in my denominator, so I'm going to do that metric conversion at the end. So again, I'm doing that N times 1 over V thing down here. Okay, so this is a molar mass. I already solved for the molar mass of silver chloride earlier. Let's see, it was 143.32. This is my mole ratio. My equation says 1 to 1. For every 1 silver nitrate, I make 1 silver chloride. Now I have all my numbers. I can solve 8.96 divided by 143.32 divided by 50 divided by e to the minus 3. I got 1.2503 something, something, something. 3 sig figs, 3 sig figs, 5 sig figs. I can have 3 sig figs. 1.25 molar silver nitrate. How you doing? Hope you're batting 1,000. I didn't give enough space really to solve this problem, so I'm going to draw a line. I want you to read this next problem and see how you would strategize a solution for it. What is the concentration of chloride ions in the final solution? What's the concentration of chloride ions in the final solution? So this question is asking me how much chloride is left in the final solution. Any concentration is, when it asks for concentration, is molar concentration. So moles per volume. If it's the final solution, then it's the final volume. Remember, we've already talked about that. That final volume is everything added up, 550 milliliters. Now this might also be instructive. I had some sodium chloride, I added some silver nitrate. Now all of the silver precipitated, but still in solution, I have sodium, I have nitrate, but not all of the chloride. I had more than enough chloride. I had excess chloride. I The limiting reactant was silver nitrate. There's chloride left over. I have to find out how much was left over. So this is NCl minus remaining, meaning not all of it reacted. Some of it stayed in solution. That's what this question is implying. Well, if I want to know how much is remaining, then probably I needed to know how many was there total to begin with. And I need to subtract the amount that I used to get the moles of Cl minus remaining. So maybe think about how can you calculate these numbers? How can you find the moles of chloride you had to begin with? And how could you figure out how much you used? Pause the video, think about it. I'll be here when you get back. Okay. Let's start with total. Where did the chloride come from? Well, all the chloride came from this sodium chloride solution, and I know its volume and I know its molarity. So I know I had 500 milliliters of sodium chloride. I know its molarity, which relates to liters. So I'm going to get out of liters and into moles of sodium chloride using that molarity so that I can relate sodium chloride moles to chloride moles. So all the chloride ions came from that solution of sodium chloride, 10 to the negative 3. The molarity was 0.5 molar. And I had 1 mole of chloride for every 1 mole of sodium chloride. So 0.25 is what your calculator is going to give you. I know I have 3 sig figs. So I'm going to add the zeros out here and tell myself this is my place value that is significant. And this has units of moles of chloride. So that was moles total. Now, how am I going to find out how much I used? Pause the video. Okay, well, how did I use it? Some of it came out of solution as the silver chloride. So I must be able to use this amount of silver chloride rather, to figure out how much chloride came out, how much I used. So I'm going to start with my tunnel of silver chloride. Again, I'm going to get into moles. So that I can relate moles of that salt that I formed to moles of the ion that went into it. 1-to-1 relationship here. Molar mass is still 143.32. Yep. So I plug those into my calculator and I get 0.0625. 8.96 divided by 143.32. 6251 something. So 3 sig figs, 5 sig figs. I have 3 sig figs in this. So this is significant to the thousandths place. This is significant to the 10,000ths place. I can only be significant to the thousandths place. I'm going to subtract this tiny number from that bigger number. And I get 0.18748, but I'm only significant to that least certain place value, the thousandths place. But this is how many moles of chloride remain. So the question was asking the molarity of chloride minus remaining. So we can take those moles, 0.18748, and we can divide by the volume. Again, this is the final solution. So that final volume was 550 milliliters, but I need liters in my denominator. So I'm going to put one more conversion factor on there. to get moles of chloride per liter of solution. Okay, so I'm going to take that number, divide by 550, divided by e to the minus 3. And I get 0.3408 something, something, something. 3 sig figs, 4 sig figs. I can have 3 sig figs. 0.341 molar chloride ions. All right. I hope that was useful in getting your brain warmed up around stoichiometry of solutions. And remember, problem solving is related. So this was a limiting reactant type problem. We have excess of the chloride ions and we want to know what's their concentration in that final solution. So we're taking that difference between what we had and what we used to find what's left over. I hope that was instructive. And let me know if you have any questions about your homework. I'll see you soon.